Hello, I want to do a practice about the heaps today because it was at first a little bit confusing to me. Let me take some notes here. Heap is a type of binary tree. For example, I have an array here. Let me take it from my other app. So this is the array I have. So how a binary tree looks like is it will be a combination of different levels, and in each level there will be the parent and the child, right? So in this case it will be something like this. For a better illustration I can show it like this. Cool. A tree will be like this, a binary tree, but of course this is not complete, right? Because when we look at the children of 4, we have the left node, but the right node is missing, so this is not complete. It's okay. Heap should not be a complete binary tree, but we said it's already a binary tree. But the rule is in a heap, all the parents should be bigger or smaller than the children, depending on the type of the heap. So it can be a max heap, which is the highest level root is the maximum, or it can be a minimum heap in which the root element or the higher level element is the minimum. So for example, this one, if this is a minimum, then if we check 2 is smaller than 4, this is okay, but 2 is not smaller than 7 as well, this is also okay, but 7 is not smaller than 1, right? So this is not a heap. At least this is not a min heap. Is it a max heap? Is 2 bigger than 7 and 4? No, this is not a max heap either. So what we can do is we can heapify this array or tree, whatever. But first of all, why do we need that? So normally, if we sort our array, then we can already have the elements in order, right? From biggest to smallest, or the other way around, from smallest to biggest. But the thing is, if we are dealing with a stream, then which means in each addition, whenever we have a new element, we have to do the sorting all the way through. And we know there are different sorting algorithms, like most of them are O n squared, or of course the efficient ones are O n log n, like the binary sort algorithms. But if we create a heap, then of course it will be even more efficient, because in each addition it will not be O n log n anymore, but it will be O log n only. Let's see how it works. So it can be a stream, or it can be a continuous picking and adding again kind of thing. For example, I get the minimum of the heap and then multiply with 2 and bring it back to the heap. So this is like I get the minimum, and whenever I put back the multiple of the minimum, I should do the sorting again, right? So in this kind of operations, let's see how we can do, instead of O n log n, we can do O log n. So first of all, let's try to heapify this. How we do is, first of all, we have to understand the index approach in the heap for the root and the children. For example, it's generally working like if we have an index I, the children would be I times 2 and I times 2 plus 1. These are the children, because each node has two children, the left and the node, right? Left and the right nodes. And normally, usually we start with 0 index, right? But if in this case, if we multiply with 2, the multiplication of 0 would cause some trouble, right? So in heaps, generally, we do a 1 indexed array. So this will be, let's say, 1, 2, 3, 4, 5, and 6 indexes. For example, for the index 1, what are the children? Let's see, for index for a value 2, the children would be 7 and 4, right? So for 1, the indexes would be index 2 and 3. 2 and 3, so 7 and 4. Correct. How about 4? The children would be 1, right? So 4 is index 3. So children would be times 2 and times 2 plus 1. So it would be 6 and 7, but we don't have the index 7. So value 1, this one, and we don't have the index 7. So this is the approach for finding the children in an index wise based on an parent or the root node index. Cool. So how we do the Heapify is we start with the last non-leaf element. So these leaves are the lowest. Let's note it here. Lowest level nodes. Lowest level means no children, right? So we start with the lowest non-leaf element. So in this case, it will be 4 and 7. So what we do is, first of all, we check, for example, let's take it here, and let's do the Heapify. So for this example, first let's do the minimum heap, and let's start with the first non-leaf node. This is 4. So we are checking if 4 is smaller than the children. It's not. So we just swap. So it will be like 2, 7, 4. At this time we will swap 1 and 4, right? So 4 will be here. Okay. Cool. It will be like this. This is the first round. And then we are done with this because there is no right node. So we complete this small triangle here. So let's check the other one as well. Is 7 smaller than 1? No. So what we do? We just swap. 1 and 7 are swapped. The other 1 and 4 were here. Cool. And we complete the swaps in this level. So we go one higher level, which is 2. Is 2 smaller than 1? No. So we just swap 1, 2, 1, 7, 8, 4. So when we see this heap, we can ensure that all the nodes have children which are bigger than that node. For example, if we check node 1, children are 1 and 2. So it is either equal or bigger. It's not smaller. If we check node 1, all the children, in this case it is only 1 with the value 4, so it is bigger. If we check this node 2, the children are 7 and 8, so they are both bigger than 2. So this is a min heap. So we did heapify operation in 3 steps, right? This was the first round, this was the second, and then this was the third round. So this was, and the length of the array was 6, right? So we did in 3 steps, 3 rounds, but it could be even 7 because we have a missing node here. The right child node of 1, I mean initially it was 4. Even if it was there, we could still do that in 3 steps, which means we can complete our operation with O log n, because we know that 3 2 to the power, let's write in this way, is 8. So for a length smaller than 8, like 7, we can complete the operation in 3 steps. Very cool. But we said that we can deal with continuous additions or deletions, right? So let's try to add some in a stream fashion. Add the elements one by one. So let's take our original array again. It was this one, right? So let's try to do this. By adding the elements one by one. So first element is 2. Okay, that's it. To the heap. So we will add the upcoming element or the upcoming value to the first missing node. So we don't have any element at all, so we just add 2 at the top. Then we have 2, so the first missing node is, of course, will be the child of 2 on the left. Okay. And then we have 4. By the way, if we are doing a min heap, then in each addition we check if it is already smaller than or bigger than the parent. So when we add 7, it is already bigger than 2, so I don't need any swap operation. Then I have 4, I add 4, and after I add, if I check if it is bigger than the parent, yes, it is. So then I don't need any swap operation because I'm doing a min heap, right? So then I have 1 here. Then I add here. It will be the child of 7. Is 1 bigger than 7? No. So what I do is I just swap 1 and 7. And after I swap this, now is 1 bigger than 2? It is not. So I swap one more time. 1 and 2. Now it's all in order, right? All the parents are smaller than the children. So how many times I have to do the comparison? I add 1 here. So first I checked with the first parent. I did the first comparison. And after 1 is here, just after swapping with 7, I have to do one more comparison. Once 1 is here, I had to compare with 2, and so I did 2 comparisons in total. Moving on, the last value that I added was 1, right? So now I'm adding 8. The next empty node is here, which will be the child of 2. Okay, everything is still in order. So I'm moving on to the next, which is 1. So now it will be the left child of 4. Okay, I add this and I do my comparison. Is it bigger than 4? It is not, so I'll just swap 1 and 4. So again, 1 is not smaller than parent, so it's okay. Even if it's equal, then it still does not violate the regulation. So everything is in order. So after I add 4, there are how many elements here? There are 6 elements, right? 6 values, 6 members of the array or of the heap. But to make everything in order, I did not have to compare this last value with all the elements. The length of the heap is 6, but I did only 2 comparisons. First, I had to compare the first parent and then the second parent. That's all. So instead of in each edition, this is the point why I would want to deal with heaps. Do not compare with all 6 members, but only parent nodes. So this is the approach how we know as divide and conquer, right? So once I have this stream coming elements one by one, I can do in a heap way, I can manage my heap by only comparing with the parent nodes by skipping all the members in the same level. Moving on, there's one more thing, which is the deletion. So let's suppose I have my heap here. And first, I delete 1. What I do is, I will move one of the childs from here to the top. And then I will check if I have to swap. For example, is 4 smaller than 1? It is not, so I have to swap. 1 is coming here and 4 is here. So now it is again still a heap, right? All the parents are smaller than children. Let's do one more deletion. For example, if I delete this one too, then again I'll do the same. I'll pick one child here and move to the top. So what I'm doing is I'm picking from the lowest and then do a top-down approach, right? I pick from the bottom and then put top and see how deep it will go. It is a top-down approach. So here is 8 already smaller than the children? It is not, so I have to swap. I swap these. But for example, I have to swap once more, right? So let me go back. So when I'm doing the swap, if I already picked the minimum, I don't have to do a swap once again. So let's pick 2 instead of 4. Let's do the swap now. Now it's okay, right? But if I pick at first 4, then 4 will be here and 8 will be here. Was it 8? I think so. So anyway, so whenever I'm doing the swap, it's better to pick the minimum so that I don't have to swap once again in the same level. So here in this level, I'm done. 2 is smaller both than 8 and 4. But I'm not done yet because 8 is still bigger than 7. So I have to swap once again. So okay, this is still a heap. And let's delete once again. Let's delete 2. So I pick this 8 and put to the top. So now I have only 3 elements with the roots 8 and then the children 7 on the left and 4 on the right. And what I have to do is I again pick the minimum Again, because if I pick 7, 7 would be going top, but it will be still bigger than 4, right? So it's better to pick the minimum. So I pick the minimum, which is 4, and swap with 8. So now it is still a heap. So in this way, whenever I pick one from the top, what I'll do to heapify once again to continuously maintain my heap is I pick one of the leaves and then put to the top and see how deep it will flow down from top to bottom. Again, the all we what we are doing is just divide and conquer. Instead of comparing with all the elements, dealing with n number of elements, just deal with log n, just with the direct vertical comparisons, and all what we have to do would be already managed. These kind of operations are already called as Enqueue or Dequeue, and we had already seen how we can do the Heapify, right? So this is, I guess, all about heaps and the heap sort algorithms.